Hi everyone, welcome to the new and improved Lush. We're a science channel now, not just gaming, science and gaming I should say. So it was going to be a long one today, but my computer hates me and we are not going to be able to get to a really deep dive on all the stuff I wanted to talk about today, which is flow cytometry, which is really, really exciting because every month they have a huge massive bulk cytometry day, and today is that day. I should also say welcome to the new Lush channel. It's not Lush Heals anymore because I do more than just heal. Lush does lots of things. She does science, she does data analysis, she yells at Google. The reason that I decided to make the switch, not just because I don't just heal in World of Warcraft anymore, but I actually am doing a course at university, and creating a scientific web presence is like my final big piece that I need to do for this course. And Twitch is a very interesting thing to choose to do this on. It's a very weird, unforgiving platform in a lot of ways. And I thought, you know what, let's see if this actually works, because there's not a lot of people that talk about science on Twitch. And I'm also going to try and answer questions that I have, like why do pharmacies take so long to fill your order? Is stress-induced diabetes real? All these things that I wish I had time to Google and find out. We will explore them together as a little science community. This may be a fail. This may just be like a 5-minute, hello, Lush is back, but she's not just playing WoW anymore type situation. All right, here we go. I'm going to swap over to my screen share in a minute, and I will introduce you to the program that we're going to use today. It's called FlowJo. Flow cytometry is a really, really cool piece of technology that we use in a lot of laboratories. You can use it to count cells, sort cells, we use it for a bunch of stuff, but it is really, really powerful. But let's just go to flow cytometry principle. We go, there's diagrams, we want a diagram. This is a half decent one. I'm going to browse in guest mode so you guys can't laugh at all of my tabs. Okay, here we go. Flow cytometry. You may say, Lush, why don't you know the answers to all these things off the top of your head? I have my answers in the top of my head. Okay, so here are some cool pictures of flow cytometry. Look at that. It's all working. You can see here, this is a decent one, all the particles flowing through a thin capillary and then being shot by the laser. And this is a typical, in our case, it'll be a cell, and they've got all these little things on the surface, right? The fluorescent dye is sticking to receptors on the surface of a cell. And that way we can figure out which cell is where, basically. And then there's forward scatter and side scatter, which come at the different sides of the cell to help you figure out how big it is, which is also really useful. Let's see if I can get FlowJo working. This will be very exciting if I can. Okay, it worked! Okay, this is FlowJo. This is a program that we use to analyze our data. And what we're going to start off with is compensation. So the reason that you need compensation, I'll just bring this back up again, is if you go to a visual representation of it, it's probably going to be the easiest way we can explain it. So it kind of looks like bell curves. So there's different colors in flow cytometry, and you can use different filters to excite the different channels, and they look like bell curves. Oh no, this page hates me. So with flow cytometry, you have different emission spectras. And then there's a peak in the middle of that where you have your maximum excitation. But you can see here that the colors are kind of overlapping, especially here with the purple and the blue. And what happens is when those color channels sort of bleed into each other, it can be quite difficult to differentiate individual populations or individual colors. So what we do is we compensate and we tidy up the bleed, the cross-channel sort of contamination that you have. I'm just going to go straight into the data analysis that I'll explain as I go along. So this is a scatter plot. These are samples that I ran last week on the machine. No, this week. And each one of these dots represents a cell or an event as they're described by the program. So this was a blood sample, and I treated it with an antibody sort of cocktail, and the fluorescent probes bound to the surface of my cells, and all of those cells will pass through that capillary that I was talking about, and they were shot at by the laser, and then we get this data here. And so each dot is a cell or an event. So this being a blood sample, this area of dots, these are our lymphocytes. And lymphocytes basically include everything, all of your white blood cells, your T cells, your B cells, your NK cells. Anywho, let's go into this population. You can sort of see now that you've gated out all that other stuff. What we're going to do now is we're going to go in and we're going to do some compensation. We're going to go workspace. No, we're going to go to tools, my bad. Then I'm just going to make a new template. And these are all the colors. Gosh, actually, I might need to do like a Q&A on flow cytometry and then do data analysis first because there's so much here that I should probably be explaining because it's not going to be making any sense. I also haven't figured out how I can explain what I do without having a whole bunch of like PETA representatives knocking on my door, basically. I'm just going to make me a little bit smaller. I think that's a good idea. You're not really here for me, you're here for the science, right? It's our first time. It's going to be messy. Oh, that didn't sound very good. What are the cells on the left going up the y-axis? Oh, you mean these ones here? That's a whole bunch of crap. And it's also doublets. So 2 cells that pass through that the machine thought there was 1. And these are beads though. This little blob here, these are our beads. We use these to quantify how many cells we have. I'll get to those. First, we're going to do compensation. This matrix that I've done has all of these things here. So the first has a little R that stands for red. Then you've got YG, which stands for yellow-green. You've got a V that stands for violet and a B that stands for blue. Those are colors. And those are these types of colors. So you have different wavelengths that we're looking at. So what I have done here is I have chosen a fluorochrome in the red channel, 1 in the yellow-green channel, 2 in the violet channel, and 1 in the blue channel. And I've put them very far apart from each other so that hopefully there's minimal bleeding. And what each of these colors are is they're a fluorochrome, which is a like little fluorescent little glowy thingy that is going to bind to a marker on the surface of the cells that I'm interested in. And I'm interested in leukemic cells in this case. So they're going to bind to leukemia markers on the surface of the cells. How cool is that? Someone invented this. I like to take a moment whenever I'm doing flow cytometry.
A few moments later.
Alrighty, so this is the first channel. This is really, really cool. This is a model where I'm using a human thing expressed. Actually, I can't explain what that is because Peter will come and yell at me again. But we're going to just start by compensating over here. Oh god, see how these curve upwards like this? That's not what you want. You want a nice, straight, clear population. It's just a nice square. So sometimes with this, I like to just throw in a really big number and see what happens. You can see down there, we're working on this square, is that it's being altered. Oh, and then the program's just going to yell at me when I do too many numbers. Right, so if we go 1, 2, 3, 4, 5, 6. We don't want it to bleed too far in this direction. That's the other thing. You want to get it nice and upright. So let's put it at 8. 8 could be good. Maybe try 10. We don't want them to drift too far to the outside. We'll start with 10. We'll start with 10. The others, this one, and this one look pretty good. You might be thinking, what are we going to do about this? We do that in a different channel. This is going to take several to get right. Now this data looks like garbage. You know why? Because I forgot to put it onto our lymphocyte gate, didn't I? There we go. That looks much nicer. Okay, so we can see this population much better now. 20 is too much. 15 is not quite enough. Let's try 17, 18. What do you think? Does that look even in the middle? I think so. The other 3 look really good. So let's just move on to the next channel. So what I'm doing is I'm trying to make sure that those bell curve peaks aren't overlapping on top of each other too much. All right, 26 was too much. 24 looks good. That looks pretty even. Nice in the middle. This one definitely needs compensating. Look at that. We'll try 10. Nah, see now when you put in a big number, like let's put in 50, and it barely moves, don't worry about it. You're going to compensate it on a different channel. Oh, okay. See how with this one, in this channel, I just put in 1. See how far all the events jump to the left? That's a lot. Let's try 0.4. Not enough. 6, 8. 8 seems pretty solid. The next one, I reckon we're just going to just bring it over just the slightest bit. I reckon we're going to do a 0.2. Ooh, what's better? 0.2. I'll put it in 0.3 and then I'll take it down to 0.1. All right, and this is another interesting thing. See how when I put in 1, the other populations moved? So what if we put in 0.2 here? We'll try 4, 6. 6 is good, and now this one looks like it's a little bit over to the left. Actually, that looks really good. We'll take that. We'll take that. This guy needs to be moved. See how he's over to the right? We'll just do 1. Let's try 10 actually. Oh, it's not great. That's better. This one also needs a little bit. And then our final channel is the 670. So you can see this population here needs a little bit. 1. Oh, too much. 4, 6, 6. Perfect. And now what I like to do now is go back to the bottom and start again. The reason I do this is because when you compensate on one channel, it can also fix up stuff in other channels. So it's good to just go back and check because maybe you've compensated where you didn't really need to. This is annoying, but I don't think we can do anything about that. This could go up to 0.2 now, I think. Actually, this program does this. Oh, 0.3 it was. Yes. All right, that looks good. So what I'm going to do now is I'm going to take this compensation that I've done, I'm going to drag it over to all of my samples, which is over here. And I'm I'm going to go to all samples. I'm just going to drop that. Doop. And you can see how there's all these little blue boxes now. That's our compensation. So we're going to go into this. We're going to delete this now, because what I want to do is I want to gate out those cells that thought that they were single cells, but they're actually what we call doublets. They're sneakies, because they're not actually single cells. They're going to trick you. So we'll go over here. So this is now looking at the forward scatter area, which is the A, versus the forward scatter height. And it's a really good way of gating out single cells. So we're just going to go like this, because we want this. There we go. I can see. We're going to call this our single cells. Beautiful. So 99.1% of the events or the cells that are on this workspace are contained within our gate, which is really good. So all of this stuff over here, this is all just debris or doublets. Go into that gate now, gated out all the other stuff. And I'm going to go to side scatter. So this gives us a really nice profile of the cells. Okay, so what we're going to do now is we're going to deal with that population that Jeff was interested in. This is the beads. I'm going to call it beads. So it's really important with any kind of data analysis, even though it's really annoying, is to have some way of quantifying or verifying your counts and your data. Because without it, even if you get really good data, how can you be sure of what is there is really there? So, and then I'm going to go into this gate. You don't even need to do this, but I like to do this. I'm going to go into that and I'm going to put in the live dead aqua channel. This is a fluorochrome that we use to differentiate between alive and dead cells, but it's really handy when you're gating for the beads. So I'm just going to call this beads 2. And you see when we go into this channel, see before, can now gate out all of this stuff that is around that population of interest. So that's why I like to go in and just make it a bit more accurate. All right, we're going to do a gate around these. So as I said before, this is a blood sample. So these are our lymphocytes. All of this stuff here that's really tiny because it's so close to being like not even existing. That's just cellular debris. That's broken up pieces of red blood cells. That's just like scraps and bits and pieces. So we want to get rid of that as well. So let's go into our lymphocyte gate. And what I'm going to do now is I'm going to look for the cells that are alive. So I put in the fluorochrome that I use to differentiate between live and dead cells. And I'm going to do a little bit of fiddling with how this looks. So let's do a gate here. We're going to call these alive cells. And I might actually customize this axis. It's over here now. So you can choose to show your data in a couple of different ways. You can choose to show it as like a contour plot, as a density plot. This is really handy if you have two populations that are kind of smooshed together. You can sort of see where the break is. You've got your zebra plot, which is also really good. Actually, as an example, you see here, see how there's two populations that are kind of smooshed together? You can drag this gate down with this. Do that so you know that you're not actually putting in any of the stuff that's below, because that's not the population that we want. But if we go back to here, I'm just going to put in some extra ticks and then look what happens with my data when I do that. It's come right up off the axis and now I can get that way more clearly. So we go back into a contour plot or even just the pretty one with the colors. You can see it's so much more neatly contained now, which is really good. I like to do a contour plot on this because I just feel like it really strongly gates out any of the nonsense. So with this live dead channel, anything that's up, that's positive for live dead aqua, is dead. So all that stuff above the main blob, we don't want it.